Welcome to a new episode of Rudy's Electronics Lab. And in recent times I've been working on BER testing, including a do-it-yourself BER PN9 generator, and also try that together with the BER tester you see here at the bottom, the Anritsu MG3700A. And in my last video I've shown that combination works well, and that we can see the bit error rate being shown properly in a number of pre-made scenarios. However, now we want to test a little bit more in live environments and with noise, etc. And the issue that I was running into, that the version of the Anritsu that I have actually only allows TTL input and not really smaller types of signals that you're typically dealing in when you want to do real life type of measurement. So what we're missing here is a sensitive input circuit, and for that reason I decided to build a comparator circuit that you see in the box right on the top here, that allows me to do certain measurements. Now in this video I'm going to show you all these measurements in a moment, but before doing so I want to talk a little bit about about why the Anritsu does not have this particular possibility right now, and talk a little bit about the choices and the design of the comparator circuit. So let's get going. Now, first, what is going on with my Anritsu? Well, if we look at the Anritsu product brochure, and you see printed the page here on the screen here, you see that it has a built-in BER analyzer, and that is really a great thing. I really applaud this. You don't have to buy any additional hardware or software option to be able to do bit error ratio measurements, etc. And that is quite unusual. Almost all the other devices that I know of, it is a paid extra. So I really applaud what Anritsu has been doing here. Yet there is something like a BER option as well, as you see here on the sheet. And that option basically relates to a higher speed BER. Now I'm not so much interested in that higher speed in my type of experiment, but actually there are a couple of other differences between the optional BER version and the standard BER version. And we learn more about that if we look into the user manual of the device, where we actually see that if you have the optional version, you can not only set the input impedance to 50 ohms, but you can also set a data threshold from 3 volts all the way down to 0.2 volts. While the standard version of the Anritsu without the option installed only accepts TTL signals. So it's really a hardware difference there as well. Like I said, I'm still very happy that the Anritsu has standard BER type of things, but we don't have these ability to measure the type of small signals that I would like to be measuring right now today. And for that we have to devise some additional circuitry to do that. Then again, it can be a bit of fun to do that as well. So let's see how we can do that. And that basically brings me to the wonderful world of comparator, because that is exactly the component you would choose if you want to go from a small analog signal to a digital signal. And unlike op-amps, comparators are designed to live at the extremes. Op-amps are typically designed to be used with a feedback circuitry and then use them within their linear region or so, while a comparator is really designed to be either at the one extreme, the one, or the other extreme, the zero, and they're optimized for all of that. So that is obviously the type of components that we want to take. So a component where if the one input gets bigger than the other input, then we have a logical 1 out, and if the one is smaller than the other, we have a logical 0 out. And that's it, so that should be easy, right? Unfortunately, it's not that easy. We have to dig a little bit into this world of comparators and how they work. And one of the things that we have to be aware of, that many of the comparators we will be using for this type of functionality have a high gain and a high bandwidth. And that also carries along the risk on erratic switching and the risk of oscillation of the comparator. And this is especially the case when we are dealing with slow changing input signals and high input impedances. And on the scope screen plots that you see here, that is some of the experiments I was doing. I was already running into some oscillation issues basically. So that's one thing you need to address. Now the good thing is that these type of oscillations are things that you can deal with. You can find information on that, how to do that on the internet. For example, you have a nice application note of Texas Instrument, the type of measures that you can take, including building a hysteresis circuit Also for comparators that don't have built-in hysteresis via a bit of feedback circuitry, you can do that, and then you really decrease those type of risks. And there are also a number of standard measures you can take, basically that would save you a little bit against that type of oscillation. Now, on top of it, you will also have to look at a number of different design characteristics, because there are different comparators on the market, and that's because they're all different in their design and their purpose and the functionality and market they try to solve. So what type of things I'm talking about? Actually, quite a lot. So put some of the on the sheet here. First of all, we got the speed of the comparator, from slow comparators to ultra high speed. We can also express speed here as delay or bandwidth. Second of all, the type of power supply. Do we have a single power supply, or do we have a double symmetrical power supply with a positive and a negative voltage rail? And also, is the power supply for the analog part of the comparator separate of that of the digital part, or are they combined? Then we got important differences in output state. Some comparators basically are rail to rail, so they will provide an output that goes to the extreme analog voltage rails of the comparator. You might have floating output, so it's like having a transistor where the collector and the emitter or something else, if you talk about other switching elements, are both floating. You might have an open drain, you might have an open collector. You also have comparators that directly have TTL output, or TTL output combined with a specific ground pin. Can also have a CMOS output, or a CMOS output with a specific ground pin with it, or combination of TTL and CMOS compatibility, etc. We have comparators with built-in hysteresis, which can be useful. Another parameters we have is the different voltage between the common mode signal and the plus and the minus power rails. Actually, some of these comparators you can feed with as much as 30 volts on their power rails, but it does not mean that their inputs can all the way go up to plus and minus 30. They may have to stay quite far away from that. And actually the comparator I'm finally using, this is the case. Then there's also differences in their differential input voltage range. So this is really the difference between the two comparator input signals here. Maybe limited. Current draw by the inputs. Unlike op-amps, comparator typically draw input current. There may be offset trim possibility with some of them. Some comparators have multiple outputs, like an inverter output. Power consumption can vary a lot. And for a lot of application, people might want ultra low power comparators, but that might go, of course, at the expense of other performance parameters here. Comparators might have strobe pins with a kind of enable pins for their outputs. They may come in single, dual or quad packages, and a lot of different form factors for their chip package as well. So, there's a lot of differences here. If you want to know more about all these differences, one good source here is the Bible of Electronics, the book of Horowitz and Hill. Actually, I probably should have started by going read this book before I did my experiments. I did the other way around, which is fun as well. But this is kind of a very good source on this type of stuff. And here you see one of the tables that you find in a book where they talk about some of these characteristics that I've just been talking about them of comparators. Now, what type of comparators have I been using for my project? I did a couple of different experiments. I started off with using a LM393, which is a very cheap jelly bean dual comparator. Actually, I had some boxes here with a lot of semiconductors here that I bought bulk, and I think there are at least like a dozen or 2 dozen of this LM393 here. But when I started playing it, I directly noticed some limitation for my application. So in the oscilloscope screen plot that you see right here, I'm feeding the device with a 100 kilohertz sine wave and compare that to the reference signal. And 100 kilohertz is about also the bit rate by which I want to be doing my experiments with that. So that's why. So I know 2 things already here that you might also see on this screen plot. First of all, the sine wave doesn't look like a sine wave anymore. It's distorted. It's clipping on the bottom. So what's happening here? I'm here powering the comparator just with a single voltage, and then you're not allowed to feed any negative voltages into it. And I'm nevertheless doing that, so it's clipping off these negative voltages. Of course, this can be solved. We can make the input signal, we can pull it up by a resistor dividing network and AC coupling, etc. But we'll need to take some measures here. Second thing that we see here is that this particular comparator is very slow. Already dealing with a 100 kilohertz signal, we already see that it really takes a lot of time basically to get to the final positive value there. We don't get any oscillation here obviously with such a slow device. But yeah, so I had to look on a little bit. And so the next one that I've been trying to go the other way is the TLV3502. It comes in a small SAT8 package, and this is a very fast comparator. Well, the fastest exists as well, but fairly fast, 4.5 nanoseconds. Again, as a single power supply, so we have to think a little bit about the input signal. It cannot be negative, or we have to create a offset there. It can directly drive CCL, CMOS or TTL logic. Played around a little bit with it. I run into some oscillation issue, been trying to figure out a little bit, but unfortunately this particular chip died when I was doing some experiment with it, so I moved on to some other chips that I still had in my lab, and I ended up using an LM361, which is a fast comparator, a little bit slower than the other one, but still more than fast enough for my purpose, 14 nanoseconds. It has a high gain of 3000. It has a dual power supply, and I like that in the end. I don't mind having to use a laboratory power supply, you know, they have multiple voltages, and this way you can easily deal with bipolar input signals, positive and negative, and I can still DC couple them and provide for the right threshold, so it becomes less dependent on frequency, etc. So I like that. It has like a TTL output with a specific ground pin, inverted output, and a couple of other things. So it's a nice chip for my my purpose. That's what ended up in my final prototype, and the circuitry of the final prototype here looks like this. And I want to talk a little bit about some design characteristics. I mean, this is really a very straightforward application of the chip anyway. I'm not adding much at all. But let me look a little bit how we're using the chip right here. So first of all, I'm not using a 50 ohm terminating resistor within my box. And why is that so? I like the flexibility of having a high impedance, a high Z input as well. And I'm simply using these feed-through terminators that you often use together with oscilloscopes as well to create a 50 ohm input. In this case, it's perfectly fine. So that's what we'll be doing here. Secondly, you see here a number of different connectors, and they're called link, and what I'm actually doing, like all the relevant input and outputs here, I'm providing an additional connector that I can link to the oscilloscope, so I can live look at the input signal, the threshold signal, and the output signal, and then I can see how it works and everything. I thought it was kind of smart to do. Later I'll show you actually there's some serious issues here, and I probably should not have done it in this way, but I'll tell you a little bit about that in a moment. What else? Yeah, so the threshold, the input threshold, and as you can see here, it must be between 0.5 positive and 2.5 positive and 2.5 negative, quite restricted. Why so? Well, actually, this is specific characteristics of the chip that I'm using here, the LM361, that does not allow like a large difference, common mode difference between its input signals. And by remaining within this range of threshold signals, you don't go above that. It's not an issue for me because I actually want to use it with small signals, but nevertheless you want to be aware of it not to damage or to destroy your chip here. And then moving on to the powering of the chip. As you can see here, I'm using plus 5 volts. So this chip can be powered on the positive REL side from plus 5 to as much as I think plus 35 or so. There's no reason for me to go higher, basically. And I'm sticking exactly at the plus 5 because that means that I can power the analog and digital REL. So that is the V plus and the VCC, respectively, power from the same 5 volts. So that makes it a little bit easier. So hence the 5 volts. While on the negative power rail, there's minus 6 volts. And it might sound a bit odd, but this is actually one of the specifications in the data sheets, that the minimal voltage for the negative rail is minus 6. The minimal voltage for the positive rail is plus 5. Don't ask me why this is the case, but there's no reason not to comply to this. So hence we're using the 6 volt voltage. Now, taking this circuit, and the end result is over here. Just a little box with the inputs and the outputs as just talked about, and of course there's very little in the box. There's basically just the chip. And there's the decoupling. Maybe I should have mentioned. So let's go back a little bit. On all the power rails, as close as possible to the chip itself, it is rather essential to do proper decoupling capacitors here to avoid undesired type of oscillation issues. So that's what I also did in my prototype. Now, this prototype works well, and we'll see it in a moment in an experiment. I also learned a little bit from it. Are there things that I would do differently the next time if I would work further on this circuit? Yeah, there certainly are. There always are. What are they? Well, first of all, these link outputs, they were actually a mistake to do it that way. Because I noted when I was measuring as these links output that I saw some noise going on and even some oscillation I thought going on. And later I realized that actually that noise was not going on in the circuit itself, but it was an artifact of the way that I created the link output. Because what did I do? I got a signal source here. It arrives at my measurement device. I terminated it by 50 ohms. And then I extend it with another cable to the oscilloscope without terminating it over there. So I'll have like reflection on this line coming back here. I'm measuring all type of things that I don't want to measure. That's not the way it should be done. How can this be solved? Well, very easy. One thing you can do is basically just take the oscilloscope signals right away, split them off from the signal source. That's what I'll do in my experiments. If you really wish to have such link output on the comparator device itself, that would also be possible, but then you probably need to do something like buffer drivers, like on-pop drivers for the inputs, and maybe a TTL driver for the output. So we got independent outputs that don't affect the device and can be properly terminated at the oscilloscope as well. What I would do different as well is next time I'll probably play around a little bit with hysteresis, either build into the, choose another comparator chip that has a built-in, or to provide a circuit for that myself via some feedback loop. That would be nice if I would be working with very slow changing and small signals. I'm not doing that really right now, so it's not really essential, but could be doing that. And next time I might experiment as well with having a amplification stage with an op-amp and with a comparator stage. I would not be surprised if that is actually the way that Anritsu does it in its optional input circuitry. But I don't know. I don't have the schematics to that, and I think nobody actually has the schematics for that apart from the Anritsu people themselves. So I can only speculate on this. But if I would do that, I might have like a separate gain control and a separate threshold control. That makes it a little bit more versatile. But that's the design that I will be using for this little video today. Now, this is my experimental setup for today. So of course we got the PN9 generator, and we got our comparator here under test, and the comparator is run here by this power supply. So we're providing plus 5 volts, minus 6 volt, and we're providing a threshold voltage which is now set at 0.5 volts. The Anritsu is going to do the BER testing. Right now it's not seeing any signal, so it's not even syncing to a PN9 signal. And I got the oscilloscope here, and the oscilloscope is basically here to test or compare the input signal of the comparator with the threshold signal and the output here. So what we see on the oscilloscope right now is that the threshold line, which is the orange line over here, is still way above the actual incoming signal. The incoming signal is low, and that is the case before because I took the output signal of the PN9 generator and I attenuated it by 10 dB to 20 dB, 210 dB attenuator of mini circuits, one of my favorite little attenuators here. So in my first experiment I'm going to see, I mean we already know from the previous video if we just use the TTL signal here it all works fine, but now we're going to see a signal which is attenuated by 20 dB and if the comparator works well. Now we see here that the comparator line is still considerably above the actual signal, so that there will be no output at all, so it's a high output. More specifically, the threshold is shown here also in its measurement windows, 490 millivolts or so that kind of is the 0.5 volts that we got over here. And when we look at the actual signal, we see it down here in the bottom. I actually have to walk here and see it. We see that out of the input signal, the lowest value of the two is 14 millivolts or so. That's very low. And the top signal is 270 millivolt here. And because 488 is bigger than 270, we're not getting anything. Now let us see if we bring our threshold down, because that should trigger the comparator. So we do that by playing with the voltage here on my, that I use as a threshold, and we should see it going down, 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 down. And there we go. If we put it about halfway, then we actually get like a output signal here. And if we go kind of close, forgot again. If we would kind of go close to here, we would get like unstable situation when we're on the low and the high side. We also would get a lot of errors coming in. But let's just focus first on the case where we should see no errors at all. Now you might be wondering, that output signal looks pretty dirty to me. Well, this is just because I'm measuring or I'm splitting a TTL signal and I'm just bringing it in here. That's a TTL signal, so it's it doesn't have a load. Should I put a 50 ohms load here, then actually the signal should be pretty clean. Yeah, there we go. We got a clean signal. But actually I'm not going to do that, because that pulls down the TTL signal so much that my Anritsu is not doing anything anymore. So while this is of course visually more pleasing, I'll refrain from doing that. I might at some point add some buffer circuit into my comparator for the scope monitoring functions, etc. Now my Anritsu is running again. So far so good. Basically we have a comparator circuit that can basically pick up a small signal, and that is properly recognized here by the Anritsu, even if we don't have the special advanced BER option available. Now, as the second part of this experiment, I of course want to use this big device over here, our baseband fading simulator, because that's a device that we can actually use to emulate different type of wideband, or sorry, of distortions on a transmission channel. So instead of using here the attenuators, we're actually going to hook up here our Anritsu. So let's see how we our fading generator. Now let's see how we do that. We take the signal that comes out basically of the PN9 generator. We're going to bring that now into the simulator, and we directly get a signal overload. So this TTL signal is fairly generous in amplitude for this function, so we need to deal with that. So what we do is that we diagram, so we go to the right option here, that's the one over here. We go to the setting, and actually there is a auto level signal. Leaving that, and after auto leveling we should be fine. Yes. So now we've automatically set the signal, and on the little graph here we can already see some signals in on the I thing. Still got no signal coming into the Anritsu, because the output is not yet configured. So we're going to put the output here, and we're going to put the output on. IQ output on, and then finally we should be taking the output signal here and bringing it into, and that should be channel A, sorry for that. And then we are getting there. So we're getting a output signal. I know this is too low to go directly, but it goes via the comparator. Again, I would need to set a proper voltage here for, yeah. And there we go. We got 0 arrows coming in. We nicely put the threshold between the values, and we got a nice TTL signal. So that means basically our comparator is doing what it should be doing. And then as the final phase, we can be adding noise and seeing some real tests basically of bit error rate being degraded over a problematic communication channel. So we do that basically by the white noise, the Gaussian white noise generator, which is right over here. And let's go there and let's turn that on. Oh, and as you can really see here, I'm inserting quite a degree of noise here. Let's make that a little bit less, because this is a little bit exaggerating. I got a signal noise ratio of only 9 dB over here, I see. So let's make that a bit of a better signal noise. I'm pumping this up here, less noise, less noise. Let's make it 20 dB or so. There we go, we're around 20 now. Yeah, so at 20 dB, I got an almost perfect signal. Sometimes I got like one error coming in or so, but again, I'm looking at 100 sequences here. So 20 dB signal noise ratio, I mean, it's a visible signal noise ratio on a signal, but the output signal is still always correct. So let's degrade it a little bit and let's go to let's say 16 dB. Yeah, and at 16 dB we do get errors coming in. We're about 2% of errors. So in 2% of the cases actually we're not picking up our signal properly anymore. If I would have even a poorer communication channel and my noise will be at, say, noise signal to noise ratio would only be 10 dB. Yeah, 10 dB, then the whole system won't even run anymore. So we need at least, sorry about that, I went through the thing. $15 dB, we got 7% of error, considerable noise. I can probably still improve it a little bit by playing around with my threshold, right? If I put my threshold right in the middle, and with my threshold right in the middle, let's try again 10 dB. Yeah, at 10 dB it still works. I get 5% of errors, pretty noisy signal. Suppose if I have a channel of only 5 dB, signal noise ratio, play around a little bit again with the threshold. Yeah, at only 5 dB signals to the noise ratio, I can still get a signal through, but it's having a lot of errors. Almost 10% of the received bits are being in error. But here I'm kind of on the edge basically, but it's still a doable signal. I mean, look at this here, you can basically see how hard it is to actually recognize the proper 0 or 1. But anyway, bottom line is that I'm very happy this comparator is doing what it should be doing, and I'm now able to test some more real life scenario, or at least simulated real life scenarios, where I can see the effect of noise on bit errors. And actually that's of course not all we can do with the device over here, because this is a very sophisticated device, so we can have lots of other distortions here. We can make kind of a linear distortions, we can have IQ factor issues, imbalances, we can do things like fading, we can do things like multipath fading and reflection, so there's so much more that can be tested from here. But at this video I wanna keep it at this. Thanks for listening. This is actually not going to be the last video, I think, on BER testing, because I got some exciting new things in mind, I hope. But they'll be there in due time. And if you're not subscribed to the channel yet, then this is your chance to do it. So, see you next time.